Welcome to a new session. Today we are going to study one application of Gauss's law. We know by using Gauss's law we can easily obtain the electric field for some simple symmetric charge configurations. Here in this video we are going to find electric field due to a uniformly charged thin spherical shell. For that, consider a thin spherical shell of radius r and charge density sigma. So, surface charge density of this thin spherical shell is equal to sigma. The center is O, and it is clear that this situation is a spherical symmetry. Therefore, the field at any point outside or inside can depend only on r, the radial distance from the center of the shell to that point, and also it must be radial, that is along the radius vector. Now we are going to consider the first case, that is electric field outside the shell. That is, we need to find the electric field at a point P outside the shell, that is r distance away from the center of the shell. That is, the radius vector is r. For finding the electric field, we can consider a spherical Gaussian surface with radius r and center O. This gives spherical symmetry. That is, electric field E has same magnitude at all points and along the radius vector. So we can say E and ds are parallel. Therefore, E dot ds is equal to E ds. Therefore, the electric flux through this Gaussian surface is closed integral E dot ds, and that is equal to closed integral E ds, and this is equal to E into closed integral ds, and it is equal to E into 4 pi r square, where r is the radius of this Gaussian surface. So we got the electric flux through this Gaussian surface. Also we know, according to Gauss's law, electric flux through a closed surface, that is closed integral E dot ds, is equal to 1 by epsilon 0 times the charge inside that Gaussian surface. We know closed integral E dot ds is equal to E into 4 pi r square, and that is equal to 1 by epsilon 0 times the q, if q is the charge inside the Gaussian surface. And here we know the charge inside this Gaussian surface is the charge of this spherical shell. And if we take charge of this spherical shell as Q, then we can write E into 4 pi r square is equal to 1 by epsilon 0 times the Q. Or we can write electric field at a point outside the spherical shell is equal to 1 by 4 pi epsilon 0 Q by r square, where Q is the charge of this thin spherical shell, r is the distance from the center of the shell to the point. We already took surface charge density of this charged spherical shell is sigma. Therefore, the charge of this spherical shell Q is equal to sigma into surface area of this spherical shell. We know the surface area of this spherical shell is 4 pi r square, where capital R is the radius of this spherical shell. Substituting here, we can get the equation for electric field. E is equal to 1 by 4 pi epsilon 0 into sigma into 4 pi r square divided by r square. 4 pi will cancel off and we will get E is equal to sigma by epsilon 0 into r square by small r square. So this is the equation for electric field outside a uniformly charged spherical shell. This equation can be represented vectorially as vector E is equal to 1 by 4 pi epsilon 0 Q by r square into r cap, where r cap is the radius vector. From this equation, we can easily say that if Q is greater than 0, that is positive, then E is directed outwards, and if Q is less than 0, that is negative, then E is inwards. Now look at these equations. It looks like an electric field at a point due to a point charge. That means it will be the same case as if the entire charge is concentrated at the center O. So we can say for points outside the shell, the field due to a uniformly charged shell is as if the entire charge of the shell is concentrated at its center. So we studied the equation for electric field outside the shell. Now we are going to study the second case, that is the electric field inside the shell. For that, consider a spherical shell of radius r and uniform charge density sigma. So, charge density of this thin spherical shell is sigma. Here we need to find the electric field at a point P inside the shell at a distance r from the center of the shell. So we mark the center of the shell as O. For finding the field at point P here, we are going to consider a spherical Gaussian surface with radius r inside the shell and center O. In previous case, we already calculated flux through a spherical Gaussian surface. With a radius r, and that is equal to E into 4 pi r square. Now we are going to apply Gauss's law here. According to Gauss's law, closed integral E dot ds is equal to 1 by epsilon 0 times the charge inside that Gaussian surface. Here we know closed integral E dot ds is the flux through that Gaussian surface, and here it is a spherical Gaussian surface, therefore it is E into 4 pi r square, and that is equal to 1 by epsilon 0 times the charge inside that Gaussian surface. Here we are considering the Gaussian surface is inside the shell. Therefore, the charge inside the Gaussian surface is 0. Therefore, into 0. Or we can write E into 4 pi r square is 0. Or E is equal to 0. That is, the electric field inside a uniformly charged spherical shell is 0. So we got E is equal to 0 if r is less than capital R and E is equal to 1 by 4 pi epsilon 0 q by r square if r is greater than r. That is, the electric field at all points inside a uniformly charged spherical shell is 0, and outside the shell it is E is equal to 1 by 4 pi epsilon 0 q by r square. Or we can write this equation as E is proportional to 1 by r square outside the shell. That is, E is inversely proportional to the square of the radius vector from the center if the point is outside the shell. So we found the electric field due to a uniformly charged thin spherical shell. Thank you for watching this video. Keep learning. If you are not yet subscribed to our channel, please subscribe it. Also, please like and share this video.